What I hope to do in this video is to give you an intuition, the reasoning, and a not a strictly rigorous proof, but a intuition behind the fundamental theorem of algebra. Before I proceed, I must give credit where credit is due. I took this reasoning from a YouTube channel called Numberphile. Might have heard of it. And this was shown by Professor David Eisenbud. So, what is the fundamental theorem of algebra? Well, suppose I have an even degree polynomial, such as x squared plus 1 is equal to 0 being the solution. Now, if I were to graph that, it would look something like this. Now, it does not seem to cross the x-axis, so therefore it looks like there are no roots, there are no solutions to that. But indeed there is, but not in the set of real numbers, in the set of complex numbers. And this was developed by Gauss. If I were to essentially tell you what the fundamental theorem is that if you have an x raised to a power, and that is the greatest power in your equation, then that will definitely have at least one root. Now, I've simplified here. The actual rule tells you that there will be n roots. There will be 9 roots in this case. But I'm not going to bother with that. I'm going to give you first an intuition. In order to really probe this, let's just get ourselves comfortable with the complex plane. So here, it's often thought of, the complex plane, as a plane. It's a two-dimensional space. So along this axis, I have what's called the set of real numbers, so 0, 1, 2, and then all the numbers in between, rational and irrational, fractions and whole numbers and whatnot. And then on the y-axis, so this is your normal number line, right? But I've introduced a y-axis, and that is the imaginary number. Imaginary numbers, the imaginary part. So you have I, 2i, 3i. So I is my unit, where I squared is equal to minus 1, minus I, minus 2, I minus 3i, minus 4i. This should be all review for you. But anyway, any point along this plane is a complex number. Right? For example, this point right here would be considered I plus 2. And it's usually denoted as a vector of that magnitude. And then this has a certain angle relative to the real number, which I'll call this right over here. That's called an argument, and this can have any magnitude you would like. So 3i plus 1, it'll be that, and it'll have this angle. Over here, you'll have this angle. So, I remind you, we have to think, what does a function do? Well, it takes you from a set of numbers, right? 0, 1, 2, dot, 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 to another set of numbers. It's kind of a link. So, if I were somehow limited and I couldn't draw my y and x axis, I could simply, in order to denote, in order to show function, I could draw two number lines, right? and I would call this the domain, whatever I plug into my function, and this would be the range, right? And for simple functions such as x plus 3, or yeah, for simple functions such as x plus 2, this dot will be linked to that right over here, and so forth. Now, why do I bring this up? Well, let's return to our complex plane. Now, because the complex number is a set encompassing real numbers, the normal polynomial function that you've seen before, it encompasses the complex numbers as well. The same scenario right over here. I have the two complex planes. This is my domain and this is my range. So my function is going to map a point from anywhere on this plane to anywhere else on this other plane. So it's the same idea with the number lines that I showed you earlier on. Before we proceed, let's take a look at the general form of a function. Now you notice that the powers are in descending order plus a constant. So I begin by asking myself, what if I make x really, really, really big, really, really huge? I'll map it on here, so it's a circle because it could be any argument, it could be any direction, any argument along here. But effectively, the hugeness of this, the greatness of this, overshadows the rest of the terms. It nullifies their effect. So over here, because it gets n times greater, or I should say to the power of n greater, the circle over here is even bigger, it's even greater. So I can kind of take my vector along for a walk, and it would kind of wiggle around here in the range. Now, what if I make x, by contrast, really, really small? In fact, what if I make it 0? Well, over here, you can see here, these terms will cancel out and I'll be left with just a constant. So f of x will be a constant. The constant can be any arbitrary point along the range. I will choose here. So I guarantee you that this point will always go there. You can think of this point right over here as effectively the y-intercept. So it's when x is equal to 0. When x is equal to 0, f of x is c. But here is when f of x is equal to 0, and this is the point where we're interested in. This is the root. Right, now let's shrink our circle down. So I'm beginning to shrink my circle down until it eventually meets the origin right over here. The same situation happens over here. It starts to cave in towards C, but at the precise moment it crosses the origin. And when it does, I catch it. There, look. That's my root. Whatever point goes onto there must be the solution to this polynomial. It can be any complex number, and of course in turn it can be a real number. Now of course there are n solutions to any polynomial, but this is the simplified version, and hopefully I've given you an intuition as to why this all works. I'll go more in detail about complex numbers next time. Hopefully this has given you some intuition about why the fundamental theorem of algebra works. So see you next time, and thanks for watching.